Started. Everyone, and welcome to our first Spotlight session. My name is Ozan Kendogan, and I'm the chair for this session. The first talk is by Divya and Somya. It's on increasing charity donations, a banded learning approach. Now, Divya and Somya, they are both in the Zoom session right now, but I think Divya has some connectivity issues. So what they did is to record the video of their talk. They'll play the recording, but they are in the room, so please utilize the chat to ask your questions. And at the end, we may have 1 or 2 minutes for live answers to some of the questions. After that, after Divya's talk, Florin will discuss this paper. I look forward to the presentation and the discussion to follow. Divya, Somya, you can play the video.
Sounds great. Let me just play it.
The organizers for inviting us to present this work in the Spotlight session. We are truly honored. Thank you also to Florin for accepting to discuss our paper. We are looking forward to your comments. I'm Divya Singhvi. Today I'm going to talk about increasing charity donations, a bandit learning approach. This is joint work with Somya, who is at USC Marshall, and I'm at NYU Stern. So before I get into this problem of charity donations and online learning, let me briefly motivate the problem by giving you some numbers about charity donations. Just in 2020, Americans donated as much as $470 billion to different charities. In fact, these donations happened by various means. This included foundations, corporations, and more interestingly, individuals like us. And 69% of these donations came from individuals. Not only this, the overall donations coming from online platforms has also been increasing. Year on year, it has seen a growth of 21%, and now it accounts for as much as 13% of these overall donations. So clearly, this is a huge market. Not only this, there is high level of heterogeneity. These donations are being made to various campaigns that belong to very different subsectors. So this includes charities from animal welfare to environment, health-based and faith-based charities and so on. So clearly this is a big market, and the underlying problem that these platforms face is that of making personalized recommendations. So what does that mean? Well, a platform might have a bunch of campaigns or charities, and there are donors that come on the platform. To ensure that large amount of donations happen, what the platform is trying to do is decide on what campaign to recommend to a donor. Now, for existing donors, this problem might be a bit easier because we know their preferences. But for a new donor, this problem becomes much harder because there's no past data that can drive the right recommendations. Let me also say that there's not just one platform, there are multiple such platforms. This includes more popular platforms like GoFundMe, but also other platforms like Just Giving, Donor, Local Giving, and so on. Now, how do platforms solve this problem? Well, they solve it using this framework of bandits. Bandits are online learning algorithms, and what they try to do is optimize the way they collect data so as to learn preferences and also optimize the recommendations. What does that mean? Well, I'll start by randomly exploring different campaigns. I'll observe user donations, and then I'm going to use this data and optimally generate this data to make optimal recommendations. So at this point, you might question, well, this is there is existing theory behind this. What is it that we are bringing new to the table? And one thing that I will mention is the existing literature makes this underlying assumption that whenever a campaign is recommended, donations are always observed. So the assumption is donors provide donations for every campaign recommendation that is made. Unfortunately, this is not true. And let me try to parse this assumption by, in fact, looking at a donor-platform interaction. So again, let's say that we have our donor. This donor decides to come to the platform, and the platform makes a recommendation. In this case, this was a pizzeria, a restaurant that was recommended. Now, from the donor's perspective, the first thing that the donor has to do is show interest or click or select this particular campaign. Once this selection decision is made, the second decision is that of donations. Now remember, from the platform's perspective, they just want to improve or increase donations, but donations only happen after a selection decision is made. What does that in fact mean? Means that donations are observed only for donors that click on the recommended campaign. So there's a large set of donors who probably visited the platform, but because the recommendation was not good, because they did not select the recommendation, there was no donation observation that was made. What this means is there's a selection bias that is going on. And what we'll try to do through the rest of this talk is try to answer, can we construct a recommendation algorithm for new donors with selection bias to maximize donations? And I hope that by the end of the talk, you'll be convinced that we will construct a learning algorithm that maximizes donations, and it will also outperform state-of-the-art learning methods in this setting. We'll do this through three main steps. In the first step, we'll formulate the personalized learning and donations problem with sample selection. In the second step, we are going to propose a new learning algorithm with near optimal regret guarantee. And then in step 3, we are going to show using synthetic and real world data that the proposed algorithm indeed outperforms state-of-the-art algorithms. Let me also mention that on the way, we'll also prove that existing algorithms completely unravel in the setting and in fact incur linear regret, which motivates actually coming up with a new algorithm. All right, so let me start by formulating the personalized learning and donations problem. And before I do that, let me also briefly mention the literature. In fact, our work lies at the intersection of two very distinct areas. One is personalization and bandit learning, and the other one is charity donations. Researchers from our community have contributed to both these very distinct areas. We believe, to the best of our knowledge, ours is the first paper that tries to bring in this personalization and learning with sample selection to the charity donations literature. Okay, so now let me start by formulating the problem and to make some of these modeling assumptions more precise. And to do that, I'll again look at a platform donor interaction. So we have our donor who comes on the platform. The platform has a set of campaigns that it can recommend to the donor. Now, for the rest of the talk, what I'll do is I'll assume that in each time step, there is just a single recommendation that will be made to the donor. In fact, this is motivated from reality. You can think of emails that these platforms send promoting particular campaigns. A lot of times, this includes a single campaign. Also, on these platforms, there's usually a centralized banner ad that promotes a particular campaign. You can think of the single recommendation as making decisions for these sorts of recommendations. Okay, so pick any campaign, and what we'll do next is represent this campaign. In fact, this campaign donor pair has a set of features. What can these features do? These features can be anything and everything that could drive the donor selection as well as donation decision. There is a large econometric literature that in fact tries to understand what features drive these donation decisions, and also shows that the two steps of selection and donation can have very different behavior. People can have very different behavior in terms of these two decisions. So for example, you can think of gender of the recipient as well as the gender of the donor, last name of the recipient, last name of the donor, the age of the recipient, age of the donor, and so on and so forth. Now recall that there are two main decisions that our donor has to make. The first decision is that of selection. And so let's say we recommend a particular campaign. What we do is we model the selection decision using a linear utility model where the unknown set of parameters are beta. So this vector is unknown because our donor is new on the platform. Then, conditional on the fact that this selection was made using this underlying model, what we do is also formulate the donation decision as a linear model. This time the parameters are beta 1. Okay, and both of them are related to the set of features that we have used to describe this platform campaign interaction. Now, beta 1 and beta 2 are two sets of parameters that can be different. What we also allow is basically some sort of correlation between these two decisions. So the selection and the donation decisions are correlated, and this correlation is basically given by sigma. Okay, so we have formulated both decisions. The next thing to think about is what is the platform really trying to do here, and what is the platform's objective. Now, in terms of platform's objective, we consider maximizing expected donations over T time intervals. And that's given by maximizing A1 to AT. A1 to AT are basically recommendation decisions. Y outcome, which is represented here at time T, is basically the expected donation that you'll observe under recommendation AT. Now, why is this objective relevant? Well, if you think of platforms like GoFundMe, the way they work is they charge a flat fee of 2.6% for every donation that is made on the platform. So the platform takes 2.6% of the donation. So indeed, then the right objective is to maximize the total donations that are happening on their platform. Equivalently, this can also be written as minimizing expected. Is this classical notion that is often studied in the bandit literature, which tries to compare the donations that are being made by our policy versus the policy of the platform, who exactly knows all the parameters and is always going to optimize or maximize donations. So just in terms of notations, AT star is the optimal campaign that can be recommended, and Y outcome is the outcome or the donation that we have observed. Now, while we consider this particular objective, I would like to say that there are other objectives that one can consider. One can think of maximizing the number of successful campaigns where success can be defined in a particular way. We consider this regret-based objective because of the GoFundMe revenue model that I just described. Okay, so the next thing now that we have set up the problem is to think of how to solve this learning problem. How can we think of learning these donor preferences? And one simple idea is to just ignore selection bias. Maybe what we really need to do is look at existing state-of-the-art learning algorithms, run them on this setting and see if they perform well or not. Maybe we don't really need to come up with a specialized algorithm. What would that look like? Well, we have our donor. The donor comes in, platform makes a recommendation. There is some donation observation that is made, which is conditional on what selection happened, whether the recommendation was selected or not. And we continue doing that. Second donor comes in, we again make a recommendation, and so on and so forth. All these algorithms, as I mentioned, are bandit learning algorithms. So they're probably trying to learn what to recommend using the data that is being generated. Unfortunately, what we prove in the paper is that any rate optimal linear bandit algorithm that incurs sublinear regret, and it is the lower bound in terms of regret, unfortunately incurs linear regret in this sample selection bandit setting. One can see that also using numerical experiments. Here are the results from this experiment. On x-axis is time periods, on y-axis is regret. You see that regret scales linearly for all of these existing values. Why is this happening? This is happening because these algorithms do not account for selection bias and in fact end up not correcting for this bias, which leads to biased estimates of the parameters. If your estimates are biased, you'll never be able to really learn the right recommendation. Okay, so now we know why these are failing. What can we do to correct this bias? What we proposed using is what is called a Heckman two-step estimator. And this was developed decades ago. And the idea is in fact reasonably simple. So we have two sets of parameters that are unknown, beta 1 and beta 2. What Heckman estimator does is it uses two steps. In step 1, we use the previous recommendations and their features that were made, but we only consider the past selection decisions. So a binary decision of whether the recommendation was selected or not. Using this data, we come up with a selection function or an estimate of selection parameters, which is beta 2. And once we have done that, we use this estimated function or estimated parameters to correct for selection bias and then estimate the donation function, which is beta 1. Okay. Let me recap a simple two-step approach because there are two sets of parameters. Step 1, use the selection data to come up with selection estimates. Step 2, use the selection estimates to first correct for selection bias and then estimate the donation function, which is beta 1. Our algorithm, in fact, uses this two-step estimator, and we propose a two-phased algorithm. In phase 1, there's random exploration. So here we randomly explore over available campaigns to generate initial data. And then in phase 2, we propose using UCB or upper confidence bound exploration with bias correction. So this phase 2 by itself has a couple of steps. And let me briefly talk about all these steps. First, we use the data that has been generated to come up with estimates of both selection and donation parameters using the Heckman two-step estimate. Then, all the unknown parameters. So these are ellipsoidal uncertainty sets of both beta 1 and beta 2, the parameters that govern selection as well as donation. Finally, we use the principle of optimism under uncertainty to recommend campaigns like one would do in a UCB type of a bandit algorithm. Okay. So the main difference here is to use the segment two-step estimator and merge it with the UCB bandit idea so that we can in fact correct for this selection bias. Now, okay, we have proposed an algorithm. The next question, which is a very reasonable question, is how well does this algorithm perform? In the paper, what we show is that if you can tune the exploration phase correctly, then the regret of the SSB algorithm or the sample selection bandit algorithm is upper bounded by O tilde of square root of t. What this means is that because the lower bound of regret in this class of problems is square root of t, the algorithm that we propose is near optimal modulo some log of t terms. Now this result we prove under a set of assumptions, and mainly there are two assumptions. The first assumption is feature regularity, which means that the features in each round, so x's that are being generated in each round, are diverse. So this is a minimum eigenvalue condition that is often used in the analysis of personalized bandit learning algorithms. And the second one is an arm optimality condition. What that means is that the optimal campaign in each time period has a very high chance of selection. So what that means is that every time period there is a donor that comes in. If I look at all available campaigns, the campaign that is the best for this donor is going to select this with very good chance. Okay, so now I've described the assumptions. Let me also briefly talk about the proof approach that we have. And the proof again is split in multiple steps. The first step is to decompose regret in terms of estimation error of both the sets of parameters, the selection as well as donation parameters. Then in step 2, we construct these high confidence sets, which are ellipsoidal uncertainty sets. Now, why is this construction a bit complicated? Because of two main reasons. One is data is censored. So recall that, as I mentioned, you do not get to observe donations for every donor. And so there's some sort of censoring that is happening that you have to account for. The second is that estimated selection parameters are used in the estimation of donation parameters. So I mentioned the Heckman two-step estimator. There we use the estimate of step 1 in step 2 to estimate donation function. And that complicates things because from step 1, we are getting something that is not exact. It's by itself an estimate of the underlying selection function. So both of these things complicate the overall proof. Now to give you also some proof intuition, here is what we really want to do. We want to learn both donation and selection parameters. If we really wanted to learn both of them, what we need is data on both donation and selection. Unfortunately, we only observe donation data after selection. So it is not that for every donor we get to observe the donation. And so what do? We ensure that our parameter estimate of the selection function is good. And we do this by a random exploration, which is phase 1. And this random exploration ensures that our parameter estimates for selection are good. Once we have this result, the next result, which follows through a series of lemmas, shows that enough data generation happens on donations in the UCB exploration phase, which is after random exploration. So informally, what this means is that donors do not select at most square root of T recommendations. So a lot of these recommendations are getting selected. Okay, this can also formally be written as a bound on the estimation error of beta 1. Okay, so let me recap and say that we started by first formulating the personalized learning and donations problem with sample selection. Then we proposed a new learning algorithm, and the main idea here was to use Hickman's two-step estimator to correct for sample selection bias, and then use the idea of optimism under uncertainty to optimize for recommendations. Now, in the last 5 minutes, let me also briefly talk about the synthetic and real-world data experiments that we did to see how well the proposed algorithm performs. And the objective of the experimental data setup is to compare state-of-the-art algorithms with the underlying SSBN algorithm under different realistic settings. These benchmark algorithms include popular algorithms like Greedy Bandit, OFUL, which is a UCB-based algorithm, and then Thompson sampling, two versions of it, in fact, prior free and prior dependent, which basically start with a prior and then update this prior and sample from this prior to make recommendations. Okay, so now I'm going to present results from multiple sets of experiments. And there's a lot that is going on this slide. So let me try to parse the result here. And there are 4 figures. Each figure corresponds to a particular correlation parameter that we've chosen. Remember, correlation here defines how correlated are the decisions of selection and donation, the two decisions that our donor has to make. On x-axis in each figure is time. So you can think of the number of platform donor interactions. And on y-axis is regret. Ideally, we want regret to be low, so lower is better. In blue color is the sample selection bandit algorithm. That is the algorithm that we propose. And then the other colors are all the other algorithms. What you see is that as we change correlation, one thing that remains constant is the fact that the proposed algorithm SSB continues to outperform all existing algorithms. And it is handsomely beating all the algorithms in terms of this regret metric. Now, instead of positive correlation, one can also test how the algorithm performs when the correlation is negative. Here are the results for negative correlation. Again, we have 4 different experiments, each with a different correlation. You see that the proposed algorithm continues to outperform benchmark algorithms even when the correlation is negative. Finally, when we construct the SSB algorithm, there are certain distributions that you have to assume for the 2 idiosyncratic noise terms epsilon1 and epsilon2. And one thing that one can actually try to test is the effect of misspecification. What if you did not really know what the underlying error distribution was? Here we misspecified this distribution and again checked how well different algorithms perform for different correlations. You again see that the SSB algorithm outperforms all other algorithms. Nevertheless, there is some decay in terms of the regret. If you compare the specified with the misspecified setting, of course, regret of the SSB algorithm also increases. In the paper, we have run multiple sets of other experiments as well that are related to other practical constraints when you think of the sample selection and how you in fact incorporate this data. And so I would be happy to talk about it, about these experiments offline as well. Okay, now let me talk about the real data experiments that we did. And this was in fact data of 560,000 individual donations that were made on GoFundMe to almost 9,000 campaigns between January 2012 to June 2016. In total, this led to donations of almost 44 million, and the median donation was around $50. Large amount of heterogeneity in this data set as well. So on the left here, I'm plotting the distribution of average donation. And you see that the campaigns that were run, so these 10,000 campaigns, different campaigns have different average donations. They're reasonably different. Then on the right, what I'm plotting is the distribution of donations for a particular campaign. So even within a campaign, there was a large amount of heterogeneity. You see that donations range from 0 to 500, which is a reasonably wide range. Now, to run our experiments, what we really need to do is come up with an experimental setup. And so in this experimental setup, we use campaign features, donor features to represent each campaign donor interaction. As I mentioned, this includes recipient's gender and last name, the donor's gender and last name, and some other features. The outcome here is the donation made by each donor. Now, one thing I'll mention here is that because this is an observational data study, we do not observe no selection in the data. We don't see what are the donors who came on the platform but did not accept the recommendation and just went away. This data set only records the donations that were made. So in order to ensure that we can actually in fact model this selection and then donation problem, we mask 50% of the donations to be able to estimate the selection and donation functions. And in fact, in the paper, what we do is we also change this 50% masking to like 75% and 25% masking. Things remain the same, or the main results continue to grow. What we see is that again, SSB continues to outperform state-of-the-art learning algorithms. They continue to incur linear regret while SSB is able to learn these problem parameters. Okay, so let me just conclude here by briefly recapping that we started with this problem of personalized learning and donation with sample selection. We showed that existing algorithms completely unravel in this setting, and based on why they were completely unraveling, we proposed a new learning algorithm that uses Heckman's two-step estimator. We showed that it performs well, both analytically and then numerically with synthetic as well as real-world data to show that it outperforms state-of-the-art learning algorithms. This concludes my talk. Thank you, and the paper is already available online. We look forward to your comments. Thank you.
All right. Thank you, Somya and Divya. So Florin will take the stage in a bit. I asked a couple of questions, but maybe we can defer to the end because I want to give Florin the stage first.
Sure, but I mean, if you guys want to take a minute for questions, I think feel free to shoot them now, and I can throttle how much time I spend. Or we can leave them till the end, whichever way.
Let's leave it to the end, and some of the questions are also easy to answer in the chat if the authors prefer to do that.
Sounds good. Okay. Hi everyone. Hope you guys are doing well. Can you see this? Can you see my slides? Okay. So thank you for the really nice presentation, and thanks to both of you for writing the paper. I enjoyed reading it as I was preparing these slides, and I learned something from it. So that's always nice. I'll try to minimize, how much stuff I repeat from what you talked about. Yeah. But I mean, from what I've read, what's the paper about and what's cool about the paper? I mean, maybe the obvious thing that's cool about the paper is that I learned about a different application and a new application. So I think this idea of managing a crowdfunding platform and maybe put it along a bigger umbrella of OR or OM for social good. I mean, it's something that I've been seeing in the last couple of years. I think it's picking up pace. I think it's going to become bigger for our community. And it's nice that you guys found a different take on it and have asked the question of, well, is there an interesting learning problem about it? And then the other thing that's cool about this is that, I mean, yeah, this is a bandit problem, it's an application of bandits, but you found one that's interesting enough that there's something new technical to be said. There's a different bandit problem that comes out of what you're doing here. And this comes from this observation that you guys had, that if you observe a user and you observe how they behave on a platform like GoFundMe, their behavior might be a little bit more complex than what traditional bandits can capture and do for you, which was this idea of having two correlated responses. There's a decision that tells you whether the user is actually going to click on the recommendation to begin with. And if that happens, then there's a different response that you want to estimate, which is how much is the user going to donate. So actually that in itself is interesting, because you have correlated decisions. The same feature could be impacting these two different responses differently, and I think that's quite nice. So one way that I thought about this paper is you can think about this as a misspecification model of the classical contextual linear bandit. So if you ask me, you told me, okay, you want to model how much people donate on GoFundMe, I would have said, okay, why don't you just run a contextual linear bandit algorithm? You try to estimate a simple linear functional of the response, and that's something that's pretty well known. And what's interesting here is that if you think about the response in your model, so in your sample selection problem, as you call it, you can think about this as a misspecified linear bandit. So this is an equation that I dug up from somewhere, I think in the back of your paper somewhere. It's kind of showing you that you can think about this as a linear reward plus some kind of funkier misspecification term. And now, if you put it that way, and if you want to work with this kind of problem, then there's two challenges that you need to figure out, and that you guys nicely figured out. A being, well, how do you account for this misspecification? Do you need a different algorithm? And if you do, how does this algorithm handle this selection bias that comes from the fact that, okay, I'm only going to observe the campaigns that have been clicked on. I'm going to deal with some kind of censor. So I think there's two particular merits that I want to single out about this. So this is something that you already talked about, but the first merit is that you are seeing that this misspecification is actually something that's costly. So I copy pasted the exact lemma, but basically what this says is, if you take an algorithm that works well for the plain linear bandit problem that achieves optimal regret there, well, it's not clear, or rather, you know that that algorithm will produce linear regret for the sample bias problem. So I think that's interesting, and you showed some empirical results as well that show that, you know, in reality this is really quite noticeable. So there's actually two comparisons to existing literature that I wanted to talk about, and maybe you mentioned them a little bit less in your review. So I thought these were two interesting ways to think about these results. One way is, you know, when I kind of realized that this is a misspecification paper, I immediately thought about a specific class of or stream of research in bandits, which was that of learning via misspecified linear models. So I think the context is a little bit different. Pricing problem, learn about demand, and then definitely, so caveat, you know, I apologize. There's so much research on bandits. It's such an active field that, you know, I think there's going to be a bunch of papers that I should have mentioned and I might have forgotten to. But one paper that I would single out there is Best and Zeevi. And there's something interesting that paper says. I think it's called something like on the surprising efficiency of, or surprising efficacy of linear models, something like that. Basically says, if you have a demand object that might belong to some kind of funky class, something that's not linear, you can still use a misspecified learning model that linearizes the demand function, and that's going to be enough. That's going to do quite well. So I thought it was interesting that your model and your paper is sort of a complement to that, because it's a paper that's saying, well, here's a different problem. There's something special about this functional and the structure of this problem where misspecification is actually quite costly. So you can't get away with linear models. The other interesting kind of stream of research is, again, if I was asked to solve your kind of problem, I would have thought about, you know, your functional is a pretty complicated functional. So I would say maybe it's difficult to do statistical learning on it. So let me just approach it as a black box and think about some adversarial bandit model. And that's, again, something that, you know, is relatively well studied, and you could have gone in that direction. But, you know, with the obvious cost that it will give you probably significantly weaker types of regret bounds and probably much worse performance. So I think that makes it even more interesting the way you guys did, is you've landed on a model that's kind of in a good zone where there's just enough linearity structure in the model that it seems, you know, sort of familiar, and there's some infrastructure that you can leverage from what we know about linear bandits. In particular, you're using this optimism under uncertainty principle that shows up a lot. But at the same time, the model is hard enough that doesn't really carry you along. It's not sufficient to just do that, and you need this new idea of debiasing via the Heckman two-step estimator. And I think that's a very novel idea, and it's something that I haven't seen in the bandits literature before. So I think it's nice how you're kind of spanning this medium between kind of a very well-researched class of models and something that's, you know, kind of way out there in terms of the bounds that you get in adversarial models. And the other thing that's interesting is that the sample selection algorithm is essentially optimal. So I mean, you're getting something that's at least up to logarithmic factors is as good as you could hope for. A couple of, you know, to say a couple of things about future directions. This slide is just a couple of small points. I mean, it's maybe more important just for you two, but I'll say it anyway. I think Ozan actually had a question about this as well. There's just one assumption that I thought was a little bit tricky in the paper, which is this assumption of arm optimal. So that basically says that there's some optimal arm where if I show the user that optimal arm, I can assume that whatever, 99% probability, 95% probability, they're gonna click on it. So, I mean, I've talked to you guys before. If I think about this as, if you talk to an online advertising person, they're going to be thinking about click-through rates, and you don't really count on 99% click-through rates. But it seems to me like this is an assumption that's improvable. So you can probably pass on some kind of parametric form with this probability. You can pass it into the regret bound. So that might be something interesting to do. Another thing is you're using this knowledge of the correlation term. Again, something where I saw that in your experiments, you have a way around this. Seems like you're almost there to just rigorously kind of remove this knowledge assumption. And maybe last thing is, I was a little bit, it seems like in the algorithm, there's this computational step of actually optimizing the optimistic bounds. It's unclear to me whether there's a principled way, once you introduce this specification, whether that's something that would remain tractable. What else? So kind of in the bigger picture of things, what did I think was nice about this paper, and what are some interesting future directions that I think come out of it? I think it's really nice that you guys wrap this around the crowdsourcing application, and I can tell that you guys understand it really well. So I can see why you did it. But there's probably a more general model here that you might want to highlight. And I mean, you mentioned that briefly in the paper, but if you think about Netflix recommendations, kind of the same thing. You click, and then there might be a different decision process for how you rate a movie. Or you click on an Amazon recommendation, there might be a different decision process for whether you buy or not, et cetera, et cetera. And in general, I mean, in marketing, there's this idea of a funnel, purchase funnel. So it'd be interesting to see whether you can generalize your model to accommodate for such a purchase funnel like this. And I mean, as far as I can tell, it would by no means be a simple generalization. It's not clear to me how you'd generalize this Heckman estimation procedure to multiple stages, et cetera, et cetera, et cetera. The other interesting future direction was, I mean, if you just look at the GoFundMe page, I mean, clearly there's some assortment that a customer might see. So I could certainly see it being very interesting to ask, okay, if the arm that you pull now becomes an entire assortment or maybe an order assortment of these campaigns, is that something that I can learn? So embedding some kind of assortment structure into the selection model is something that could be quite interesting to do. And again, there's a question of how robust or how flexible is this Heckman estimation approach to actually handle a multidimensional structure. And obviously, too large of a stream of literature to mention here, but lots and lots of people that are working on customer choice, on assortments. There's a lot of new stuff on product ranking. So it'd be interesting to kind of take a next step and kind of contextualize what you guys are doing here into that kind of literature and think about the impact of assortments and learning assortments there. So yeah, I mean, like I said, I think I learned something from this paper. I think you guys have a really, really nice model for this. Looking forward to seeing more work in this area and seeing more papers from you guys. So I think I'll stop here and leave a minute for questions.
Thank you so much, Florin. I really like your discussion, especially the connection to the other work related to misspecified models. So we have only 1 minute for questions. If someone has a really quick question, please go ahead and ask it. You can also utilize the chat. By the way, at the end of the session, we'll go back to the room and we can continue our conversation there as well. Is there any very quick question? I don't see it. In the meantime, Anand, would you like to set up? Would you like to try sharing your slides?
Sure, I'll just do that.
Okay, so I don't see anything in the chat. So let me just thank both the speaker and discussant, both Florin and Divya, for the excellent presentation and the discussion. We'll move on to the second talk of the day. We'll hear about dynamic learning in large matching markets. Anand, the floor is yours.
Of course. Just before we get started, I hope everyone can hear me clearly and you can see the slides also.
Yes.
Perfect. So, all right. Hello, everyone. My name is, before I start, a big thank you to the organizers and the jury for the opportunity to present our work in this session. My name is Anand Kalvit. I'm a PhD candidate at Columbia University, and I'll talk about dynamic learning in large matching markets. This is joint work with Professor Assaf Zeevi. So the online bipartite matching problem, it's a very classical formulation in theoretical computer science that sort of that dates back to the early 90s. And the problem basically involves a set of jobs arriving sequentially in time, which must then be sort of routed or matched to a set of waiting workers or agents. The perspective that we take on this problem is basically sort of, it differs from these classical formulations in two ways. So first of all, we consider a novel variant of the matching problem where upon arrival of any given job, the edge weights are unobservable. The decision maker can only observe a sort of noisy bandit feedback of the associated edge weights. And also what we're doing is we are considering a large market regime where the number of workers or the number of agents in the market is substantially larger relative to the time horizon of the game. So this basically sort of introduces this aspect of choice overload in the market. So in a nutshell, the salient features of this problem are that jobs arrive in batches of stochastic size and composition at times indexed by little t. Each job must be matched upon arrival to a worker from an infinite population of available workers, with the caveat that the worker types are unknown a priori. Now, as is the tradition in settings with imperfect learning and incomplete information, we assume that each match executes in one period and generates a stochastic reward upon completion. And we're interested in the classical goal of maximizing the cumulative reward accrued over t rounds of matching. I think this particular aspect I already touched upon previously. We're sort of interested in this aspect of large markets where the decision maker is faced with a choice overload in the sense that the number of workers available for a selection is this number overshoots the time horizon t. So what actually happens is the population of workers is governed by a latent type distribution, which the decision maker is oblivious to a priori. All right, so going into the specifics of this model, what we have is on the demand side, we assume that jobs belong to a finite universe of types denoted by calligraphy J. They arrive in batches of stochastic size and composition, and the types and multiplicities of jobs are perfectly revealed upon arrival. In particular, lambda subscript j comma t, jobs of type j arrive at time t, and one can imagine this vector of demand being sampled from some underlying distribution that the decision maker is unaware of a priori. And the samples are basically assumed to be independent across time. So what does the decision maker know in the setting? No ex ante information on the underlying distribution that governs the generation of the demand process. Okay, so that was on the demand side of the market. Now what happens on the supply side? So we model each worker as being characterized by some latent vector of types, which is sampled from, again, another latent distribution D, which sits in the card J dimensional ambient space. So the interpretation here is that the jth component of the type vector tau basically lies in this index set 1 from kj. So for instance, if the jth component of the tau vector is equal to I, will simply refer to that worker as being of type I with respect to a job of type j. Now, at a distribution level, the proportion of type I workers, this is with respect to type j jobs, in the population is given by alpha sub I comma j, and the sort of the bold vector simply denotes the sort of the vector representation of these probabilities. We assume that type I workers with respect to type j jobs generate a mean reward of mu sub ij per match. And then these are just some sort of a standard notation, which I'll be sort of coming back to through the course of the talk. Again, as a standard, rewards are independent across matches and in time. And in terms of what the decision maker knows a priori, so we consider a very generalized setting wherein the decision maker does not have any ex-ante information on either the underlying distribution D that governs the, or rather controls the proportion of different worker types in the population of workers, nor does the decision maker have any information on the statistical properties of the generated rewards. So what does the decision maker know then? So we assume for simplicity that the cardinalities kj's are actually known a priori. Now, what is the interpretation of kj here? So kj simply means that for a job of type j, there are kj distinct subpopulations in the pool of available workers. And each of these subpopulations is characterized by a distinct mean reward. So that's like the general setting that we are looking at. Is there a question about the modeling sort of fundamentals or any primitives at this point?
No questions in the chat.
Perfect, perfect. Thank you. So in terms of admissible controls, what are we looking at is, so the decision maker at any point of time will be faced with two choices. She can either match an incoming job to a worker that has matched before. So this would be some worker that has some sort of previous match history associated with herself, or the decision maker can simply sample a new worker, an absolutely new worker without any history of previous matches. And this will be sampled from the underlying distribution D. I'll reemphasize that the decision maker has absolutely no idea of what this D actually looks like. Now, as one can imagine, because there are like infinitely many competing alternatives, because you have an infinite population of workers, the choice between 1 and 2 is non-trivial. And this is especially so in light of the fact that there is no information on D available a priori. And these decisions have to actually be implemented in a data-driven manner, meaning that the policies have to be adapted to the current filtration. Okay, so what do we aim to do with this? So we basically want to sort of design adaptive policies that are in some way able to compete with a clairvoyant benchmark. A clairvoyant in this case would be basically a full information setting where for each arriving job, an optimal match is prescribed. Right. So that basically leads us to the sort of following formulation of the optimization problem that we are interested in. So it's a cumulative regret minimization problem. There's 3 summations. There's a lot of things to unpack here, so I'll go over things sequentially. The outermost summation is natural because we're interested in the cumulative metric. The time index simply sums over the horizon of play. The summation in the middle is over all possible job types that exist in this universe of possible jobs. And the innermost summation is with respect to the multiplicity of jobs of a given type that arrive at a given point of time. So if you recall, lambda sub j comma t is the number of type j jobs that arrive at time t. What is this term here? This is simply the difference between the optimal instantaneous reward that could hypothetically have been generated if I had full information about all worker types, minus the mean reward associated with the worker that I actually end up routing that particular job to. So it's a well-studied notion of instantaneous regret, which is then basically summed over the horizon of play to give a cumulative regret metric. All right, so I'll claim at this point that the core complexity of learning in this matching problem, in this matching formulation that I just described, resides in a simpler formulation, which I'm going to refer to as the basis problem, where the the demand process is sort of deterministic and homogeneous. So it suffices to sort of just do away with the stochasticity in the demand process, assume that we have only one job of a unique type arriving at each point of time. And furthermore, for the sake of illustration, I'll assume that there are only two types of workers in the population of available workers. So this might already sort of give you a sense of what the problem actually is going to be very similar to, or what basically underlying connotations it has. So the key features of the basic of this basis problem that I introduced on this slide are that jobs of a fixed type arrive one by one. There are only two worker types in the population, each characterized by a distinct mean reward and a gap of delta, and a fraction alpha of optimal workers in the population. Now, the decision maker knows that there are only two types of workers in the population, or there are only two subpopulations, but she's oblivious to all other primitives that govern the statistical complexity of this setting. So this basis problem is what we are going to refer to as the countable unbounded problem going forward. So how does this countable unbounded problem compare with standard learning paradigms? So what I'm showing you on this particular slide is nothing but a classical A/B testing sort of scenario. You have a classical stochastic two unbounded problem. There are two competing alternatives, and you basically have to maximize the cumulative reward over a sequence of t plays. Now, the countable unbounded paradigm that I introduced previously, this can be generated by replicating each of these two competing alternatives an infinite number of times under an arbitrary relative scaling, which is basically captured by the constant alpha. So that's how you basically generalize the standard finite unbounded problem to its countably many-armed variant. Now, based on this generalization, it is natural to expect that this new problem is it has to be in some way statistically harder than the classical finite unbounded problem. We indeed show this via certain careful information theoretic reductions, which are to basically sort of take care of the combinatorial complexity arising as a consequence of countably many arms. So it's basically a result which offers a sanity check at a certain level. It says that the regret grows logarithmically in the horizon for well-separated instances. However, there will exist some instance at which it's somewhat unavoidable to incur a regret that grows at least as fast as square root t. Classical information theoretic sort of lower bounds. However, as you can observe from the structural form of this result, the information theoretic reductions that we used here, they fail to capture explicitly the dependence with respect to the parameter alpha, which is a key driver of the complexity of this setting because it controls the fraction of optimal workers in the population of available workers. To explicitly sort of characterize this dependence with respect to alpha, we sort of restrict to a somewhat, we shift our focus to a somewhat restrictive, yet fairly representative policy class, which basically operates on this principle of collecting enough arms at the outset. Let's say I collect 1,000 arms at the outset, and then I optimize on this set of 1,000 arms that I collected initially. So any and every policy that operates on this particular principle is what I'm going to call as a memoryless policy. And we show that for memoryless policies, it is sort of impossible to avoid incurring regret that scales sort of that has a so it's basically unavoidable to sort of incur regret that doesn't have a 1 over alpha dependence in the leading logarithmic term. So this is already something which we see is fairly different from what happens under classical information theoretic reductions. And the alpha dependent lower bound proof it's sort of novel in the sense that it does not resort to any change of conventional change of measure techniques or information theoretic reductions that are principally used in all classical results. Instead, this result exclusively depends on certain novel ideas from convex analysis, which I'll be happy to discuss offline. All right, so having sort of discussed the basics of what the lower bounds for this problem might look like, What are some natural challenges to algorithm design in this setting? So as I alluded to previously, absent information on alpha, quantifying enough is challenging. And this enough has to do with what is the right size of the number of arms that I need to sample upfront in order to achieve a rate of regret that is optimal in some sense. So how can we do that in this problem? Absent information on alpha is not obvious at all. So in particular, what this means is if the set of collected arms does not contain the optimal mean reward, then linear regret is unavoidable under any algorithm. This is intuitive. This is pretty natural to sort of imagine. So this aspect, this additional layer of complexity basically necessitates sampling new arms from the population of available arms in an adaptive manner. Now, what exactly is this adaptive manner is something I'll sort of touch upon in subsequent slides. So the natural question here is, absent information on all of the primitives in the problem and endowed only with the knowledge of K, can we sample arms adaptively from the infinite population of arms in order to recover a regret that grows near optimally, let's say, in the horizon? The answer to that is, in fact, yes. We in fact developed two strategies based on very classical principles, which are primarily used for finite arm bandits. So the first one is the idea of optimism-based adaptive exploration. This basically uses upper confidence bounds. We extend the classical UCB algorithm for finite arm bandits to the countable arm bandit setting, which I introduced previously. But then that runs into certain limitations, which I'll sort of briefly touch upon later. And so in order to sort of get rid of those limitations, one needs to come up with adaptively determined exploration thresholds. And that basically corresponds to this adaptive explore then commit policy, so countable arm bandits. So I'll quickly introduce what a sort what the structural form of any algorithm which is tailored to the countable armed bandit setting looks like, and how it differs vis-a-vis conventional finite armed formulations. So what this algorithm basically does is that because it knows that there are only two subpopulations, it samples two arms from the infinite population of available arms. Now, two suffices precisely because there are exactly two types of arms in the population. You need not sample anymore. Now, on this sample consideration set, the algorithm is actually going to play a policy that looks like UCB. However, it will nest UCB in a certain careful manner. And this is something which I'll explain here. So on the selected consideration set, which basically is sort of denoted by calligraphy A, what the algorithm does is it compares the cumulative reward accrued across the two arms. So the term in blue, the factor in blue, can be ignored for the purpose of this talk. It's just a zero mean noise term that I'm adding for stability purposes. But otherwise, if you take a look at the functional form of this statistic, it is just the difference between the cumulative reward accrued across the two arms, right? What I'm going to do is I'm going to compare the value of this statistic against a threshold, which basically grows as 4 square root m log m. And if the statistic is smaller compared to the threshold, I'm just going to discard the consideration set of arms and reinitialize my algorithm from scratch. Now, why is this necessary? You can think of an event in which the two arms that I started out with initially both correspond to the inferior mean reward, right? So you have an optimal population, you have a suboptimal population. By sheer bad luck, you happen to sample both the initial arms from the inferior population. So in that case, any and every algorithm that sort of is restricted to such a consideration set will incur linear regret in the horizon. So one needs to get rid of these bad consideration sets as soon as possible. And that is precisely achieved by this hypothesis testing step here. Now, in case it is found that the value of this statistic overshoots this particular threshold, the algorithm simply resorts to playing the vanilla UCB policy. This is nothing else but the classical UCB policy, dating back to 2002. And the entire process basically repeats, in a similar manner. So what we're actually able to show for this policy is that its regret grows logarithmically in the horizon. So it is rate optimal in terms of its dependence on the horizon t. However, there are two sort of factors which are distinct in this upper bound if you compare them to classical upper bounds for finite arm problems. One is the presence of the beta delta factor in the denominator, which basically corresponds to an additional layer of complexity which is introduced in the countable arm setting on top of the finite arm setting. And this is precisely something that encapsulates the fact that you have infinitely many competing alternatives for each type as opposed to only finitely many. So that is one non-trivial distinction. The other is that the dependence on alpha, which encodes the fraction of arms of the optimal type in the infinite population of arms, that dependence is surprisingly only of a constant order. So as you can see here, there is no alpha that features in the leading logarithmic term. So this is something which is quite unique to this setting and marks a very sharp point of departure from what classical upper bounds for finite arm bandits look like. Now, the workhorse here is basically a novel concentration property of UCB algorithms that facilitates basically the analysis here. I'm not going to touch upon what the result specifically looks like, but I'll be happy to discuss that offline in case anyone is interested. However, although we do have this very nice property holding for the case of there being exactly two types of arms in the population, the concentration property of UCB that I alluded to previously, it fails to generalize these logarithmic bounds to situations where there are more than k types. Oh, sorry, situations where there are more than two types in the population of available arms. So we need to basically sort of come up with a new design that somehow is able to sort of circumvent this issue around k being 2. So we basically propose a sort of a nested explore then commit policy that mitigates this problem. I mean, what it actually does on a very high level is structurally similar to the previous policy that I showed you. The only difference is that the UCB update step, which corresponds to step 9 and 10 here, is replaced by an explore then commit style step here. So that's structurally the only thing that is different between this algorithm and the previous one. And for this particular algorithm, one can actually show that its regret also scales in a manner which was identical to the upper bound for the UCB-based algorithm. And on top of that, this policy actually is able to generalize logarithmic bounds also to settings where there are more than k subpopulations, where there are more than 2 subpopulations in the set of available arms. All right, so what we did in a nutshell was we basically leveraged algorithmic ideas from the classical stochastic 2-arm bandit problem, right? To guide design principles for the countably many-armed extension of the finite arm problem, right? And this was basically achieved by the 2 algorithms that I showed you previously. The next step naturally involves sort of elevating these performance guarantees to the full generality of the matching problem that I introduced at the outset of my presentation. So how do we actually do that? So this is actually achieved by a meta algorithm that we call match. I'll not go into the specifics of what this meta algorithm actually looks like, but in a nutshell, this meta algorithm basically calls the previous 2 algorithms that we saw as subroutines, and these subroutines are basically invoked in a parallelized manner. So what that basically leads us to is the following regret upper bound for the matching problem in full generality. So the regret of the policy given by match after t rounds of matching is bounded logarithmically in the leading term, basically the leading horizon dependent term. And there's an additional sub-logarithmic term, which again sort of captures the dependence with respect to the proportion of sort of worker types in the population. So this is something which also featured in previous results for countable armed bandits. The takeaway here, or rather the sort of the message here that I would want all of you to sort of focus on would be that even though the problem is, I mean, in simple English, even though the problem is like infinitely harder compared to a finite unbounded problem or a finite matching market model, the dependence of achievable performance or the dependence of achievable regret and the problem on the distribution of workers in the infinite population of available workers, the dependence is surprisingly only of a sublogarithmic factor. We in fact conjecture that this log of log t term is perhaps only an artifact of our analysis, and we conjecture that this can in fact be improved to a constant order dependence. Like there's no dependence on a time horizon t here, but that's one direction which is left to future work at this point. So with that, I would sort of quickly summarize my talk here. So what we did in this work was we came up with a new matching paradigm for large markets with simultaneous matching and learning. So this has a component of matching naturally, and there's also a component of learning because the edge weights associated with worker and job type pairs are unknown a priori, but these can be learned over time based on a noisy bandit feedback. The key insight that our theoretical results here provide is that achievable performance in this problem only has a sublogarithmic dependence or a second order dependence on the distribution of worker types. And this is something which we speculate is unique to this particular large market setting. The theoretical results in this work are founded on certain novel elements of analysis that may be of independent interest. Again, I'll be more than happy to sort of discuss those online. And on a related note, there are many there's a plethora of related open problems that sort of pop out as a sort of as a side note of the modeling and the analysis that we have done in this work. So I'll be happy to discuss any and every of these questions if anyone is interested. So I'll conclude my talk with that, and just a quick passing remark. This is very much a work in progress. So comments, questions, criticisms, all the more welcome. And this is basically a sort of very recent sort of line of work that we have been pursuing, and happy to take questions at this point. Thank you.
Thank you so much, Anand. If there are quick questions from the audience, you can use the chat or unmute yourselves and ask the question. Let me pause for a second in case there are. We are going to proceed with Ali's discussion in a bit. All right. I mean, let me just briefly say the following, Anand. Like I think you've described how match works at a very high level. One thing I was wondering is if you can give us a little bit more flavor of how it uses these other algorithms as subroutine and what's like critical in the analysis step. I don't know if this is something Ali will touch upon, but maybe if you don't mind, we can hear from you and then move on to Ali.
Sure. So what I did was I gave a fairly sort of high-level idea of what a sort of a typical algorithm for a countable unbounded problem would look like, which is basically the problem captured by the cartoon on this slide. Now, the natural next step is to extend or sort of invoke these algorithms as subroutines so that you can solve the matching problem in full generality. So what match actually does is that for each job of a given type, it calls a separate instantiation of an algorithm for the countable unbounded problem parallelly. Right? So what that actually leads to is that at any given point of time, there are stochastically many threads of an algorithm for the countable unbounded problem working in parallel. Right? So what happens is that the cumulative regret is basically just stacked over these stochastically many threads, and so you at the worst you incur a loss that is of a constant order. So that's how one is able to translate logarithmic guarantees for the countable unbounded problem to the full generality of the matching problem. So this additional summation over the job types, which is here, this is introduced as a consequence of match invoking these algorithms as subroutines in a parallelized manner.
Perfect. Thanks so much for expanding on that. In the interest of time, let's move on to Ali. Ali, do you want to try sharing your slides?
I think you need to let me share my slides. Yeah, perfect. Thanks.
I don't see the slides yet. Here we go. Perfect. I see your slides now. Ali, thanks so much for discussing this work. The floor is yours.
Perfect. Thank you so much. Thank you, Anand, for a great talk. And hello, everyone. Thank you for being here. And a special thanks to the organizers for a great set of talks and for having me as a discussant of this very interesting paper. So I really enjoyed reading the paper, and hopefully, I can convince you at the end that this is an interesting paper. So I'm going to start with a sort of a high-level description of the application, and then mostly I'm going to focus on the sort of fundamental, online learning problem that this paper is dealing with. So what's the application? So we're going to have a set of workers with k different types, and crucially infinitely many workers of each type. So that's one of the key assumptions. And then there will be a sequence of jobs that will arrive over a time horizon. And for now, I'm going to focus on having only a single type of job, and the essence of the problem is just extends to multiple jobs as well, because basically things decouple here in this setting because we have infinite supply of workers. And then what happens is the platform can either drop the job or match the job to a new worker, sampled from this pool of workers, or to a worker that has matched before. So these are the actions of the platform. And the thing is, each worker type is going to generate a random reward with some unknown mean. So again, so something to highlight here is the types of workers are hidden, so the platform does not observe that, and the platform can sample sort of new workers from this pool of workers, and again will not observe the type of that worker. It may be of the same type that already has matched before, or it may have a new type, so the platform has no information about that, so that the platform does not see the label of the worker, does not see the sort of type of the worker. And the contribution of this paper is to sort of naturally formulate this problem as an online learning problem in terms of a novel variation of multi-unbounded problem, and essentially solving it, providing some bounds on the regret and providing sort of matching lower bounds for that as well. So that's all I want to talk about for now in terms of the application. I want to mostly focus on the sort of abstract online learning problem that this paper is dealing with. To introduce that, so let me start with the classical setting, like the classical setting of the multi-unbounded setting, and just to introduce some notations, and later I will talk about the sort of novel twist of this paper. So in a classical setting, we have k distinct arms with unknown mean, and let's say bounded 0-1 reward. And then what happens is that we want to devise a strategy that minimizes the expected regret. And the expected regret is going to be simply the expected mean of the best arm in the hindsight minus the expected reward of any policy that we're going to choose. For instance, if we have a time horizon t in the first round, I'm going to pull one of these arms, so let's say pi1, and I'm going to use that history, and then pull another arm, pi2, observe another reward, and then at each time t, use the history up to time t to decide about the next arm I want to pull, all the way to the end of the time horizon t. And again, the goal is to sort of minimize the expected regret. So that's the classical setting. Now let's look at what this paper is dealing with. So the problem that this paper is dealing with, so they call it the countable arm bandit, or CAB, in short. So again, we have a set of arms, and they have, there are k distinct types of arms, again with unknown mean rewards. So up to now, everything is similar to the sort of a classical multi-arm bandit setting. But here's the main difference. So the types of arms, if I draw some samples from this set of arms, the types of arms are going to be hidden. And they're going to be drawn from some unknown and underlying distribution. So I do not see the label of these machines. So what that means is, we may end up having a situation. For instance, if I draw k samples from this set of arms, so what can happen potentially is, for instance, the first two machines have the same type, for instance, and I have no prior information about that. So I have to, if they have the same type, I have to learn that along the way. The other thing is, the optimal arm may not exist in this set. I may be, unlucky that, the set of arms that I've, sampled from the set of arms, does not contain the optimal arm. So, things are not, that easy. And again, so one other, distinction is, unlike the classical multi-arm bandit setting, there are two set of actions here. So one is, pulling an existing arm. The other one is drawing a new arm from, this set of arms that we have. And again, once I draw a new arm, there is no, I don't see the label of that, and there is no guarantee that it will have a new label. So again, what is the goal here? The goal is to devise a strategy that minimizes the expected regret. So what's the main difficulty? So as I mentioned, so the main difficulty is, if I draw some samples from this set of arms, there is no guarantee that, the set of arms I'm working with contains distinct mean rewards. They can all be from the same type, if I'm very, very unlucky. And what that means is that there is no guarantee that the set of arms we're working with contains the optimal mean reward. So there is no guarantee in the sense that I have to sort of guarantee that the optimal one is included, and there are ways to do that. And the reason is this key assumption here. We know that there are k distinct arms, so there is some hope. What that means is, if I can sort of guarantee that I'm working with k distinct arms, I can make sure that the optimal one belongs to that set as well. That's the key. So this having k distinct arms is a key assumption, which sort of enables working with this setting. Otherwise, there is no hope of moving forward. So now, one natural question is, can we extend the existing algorithms for the multi-arm bandit setting to this, new setting of countable arm bandit or CAP? So the first algorithm that comes to mind is UCB, and the answer is no in general. You can extend it for K being 2, but beyond that, so one cannot simply extend UCB for multi-arm bandit setting to this new setting of CAP. Then you may say, well, how about some other algorithm? There are some other algorithms for the multi-arm bandit setting. Perhaps one can extend one of those, and the authors have found one of those algorithms. It's called explore then commit, or ETC. So let me first introduce ETC for multi-arm bandit setting, and then later I will tell you how one can sort of extend this algorithm for multi-arm bandit setting to the setting of the paper CAP. So what does this explore then commit algorithm do? It has a very sort of simple principle. Says, look at the sample mean of each one of the arms at time t. And then if all arms are distinguished enough, then commit to the arm with the highest sample mean. Otherwise, we're going to pool each one of the arms, once again, and add to the samples that we have collected. So it's very simple, and this bound here, there are some reasons for choosing this particular choice. It serves two purposes. It has to be small enough so that we commit sort of early on, so we're not incurring a lot of regrets. And it has to be large enough so that once we commit to the optimal. So again, once we figure out that these arms are distinguished enough, we're going to commit to the one with the highest sample mean. So that's the very simple logic of this explore then commit algorithm. So now, before telling you, how does this extend to the setting of this paper, let me tell you, the performance guarantee of explore then commit for the classical multi-arm-banded setting, and then we will be able to sort of contrast it with the results of this paper. So what's the performance guarantee of explore then commit algorithm? So if I haven't made a mistake, so here is the performance guarantee of explore then commit algorithm for multi-banded setting. So the key thing here is there's this constant term. So if I put that aside, there is this log t multiplied by this other term. And this thing here, the important thing is this delta I. That's the difference between the optimal mean reward and the reward of arm I. And the reason for having 1 over delta I here is actually quite natural, because if this is small, it will be harder to sort of distinguish arm I from the optimal one. So how one can prove this performance guarantee? So with a high probability, so one can show that we will commit after log t rounds, and then once we commit with a high probability, we have committed to the optimal arm. And once you put these together, you will get this sort of regret bound for the explore then commit for the classical multi-arm banded setting. Now again, going back to our question, so can we extend this strategy to countable arm banded setting? And the answer is yes. But before that, let me tell you, what was the main challenge of CAP? Let's recall that. So the main challenge is we do not know if the set of arms we have drawn so far contains the optimal arm. So that's the main challenge. But again, remember the key assumption, we know there are k distinct arms. So what that says is, if we make sure that we have k distinct arms, then the optimal one is included in this set. So how can we formalize this idea? So there will be, another exploration phase on top of the, explore then commit algorithm. So here is the sort of exploration phase that we need, on top of the typical explore then commit algorithm. So it says, we're going to draw some samples, the k samples from the set of arms. We're going to form the sample mean of each one of the arms. And then we see whether we have k distinct arms or not. So here's the criteria. So I'm going to explain that in a second. But if we do not have k distinct arms, then we are going to discard all arms, reset the whole process, sample again k arms from this pool of arms that we have. So we're not going to recycle anything. So again, if at any point we figure out that we're not working with distinct arms, we're going to discard all of those and then sample k new arms from the set. And if that doesn't happen, then we're going to basically run explore then commit. So we're going to see if arms are distinguished enough, then we're going to commit to the arm with the highest sample mean, and otherwise we're going to pool each one of the arms and add to the samples we have collected so far. So again, this top part is the additional step that one needs on top of explore then commit. And the reason for including that is to guarantee that we're working with k distinct arms, and therefore the optimal one belongs to this consideration set that we're considering. So now how do we figure out whether
2 minutes.
So how do we figure out whether we have k distinct arms or not? So I'm going to look at the samples mean, and if they're close enough to each other, then I'm going to decide that they're statistically the same. So I'm going to discard those. But things are not that simple. So if you simply take the difference of these two, things are not going to work. And what paper beautifully finds out is if you add like a normal noise there, or sort of any unbounded support noise there, then things are going to work out fine. So here's the performance guarantee of this algorithm. So I need two more notation to sort of explain the upper bound. So one is this small delta, which is the smallest gap between the reward means, and large delta, which is the largest gap. So before explaining each one of the terms in this bound, let me tell you again how one can prove this. So remember, there is this additional layer on top of explore then commit. So one can show with a high probability we will find k distinct arms early on. And then once we do that, the rest of the proof is similar to that of multi-banded setting. However, it requires developing sort of novel concentration bounds, and those can be of independent interest. So it's there are several non-trivial steps there, several super interesting concentration bounds that can potentially be used in other problems. All right, so now let's have a closer look at this upper bound. So one thing that Anand also highlighted in his talk is the main difference between this variation of multi-banded setting and the classical one is the fact that we do have these alpha ones, this alpha i's. So we don't know the type of arms, and they're drawn from some underlying distribution. But what we see is, I'm looking at this regret. These alpha dependent term is a constant. There's a second order term. It does not multiply by log t. Even though that's the main difference, interestingly, the alpha dependent term is not a second order term. And one can see as these alpha i's becomes smaller, the bound increases. That's natural because sampling distinct arms is going to become harder. And the other thing is the dependence on delta, and the fact that as this delta becomes smaller, the regret increases, and that's quite natural because distinguishing the arms is going to become hard. Now, here's the upper bound, and the paper provides several interesting lower bounds to match this upper bound. Here is a summary of some of those lower bounds. The dependence on t is optimal, so this log t dependence is optimal. The dependence on delta is optimal, and the dependence on alpha here is constant. And if you consider the class of memoryless policies, the dependence on alpha is going to become first order. So there is some interesting contrast between the policy that this paper proposes and the class of memoryless policies as well. And one thing I want to highlight again in terms of the proof techniques for the lower bound, there are several novel techniques there that can be of independent interest. So there are information theoretic and change of measure techniques, but on top of that, there are super interesting ideas from convex analysis as well. All right, so I'm pretty much done. So let me recap and then talk about some future directions. So the paper studies an interesting and important application in the context of matching workers to jobs. So what I find most interesting is the fundamental online learning problem that is novel and potentially of broader interest. And the proof techniques are also super novel and potentially applicable to other settings. And in terms of future directions, I think if I think about the application side, extending the results to sort of matching when supply is large but finite, can be an interesting future direction to explore, because in that setting there will be competition among jobs. Things will not decompose anymore. And the other thing is, again, because this sort of variation of multi-banded setting is interesting by itself. I'm wondering, if there are some other applications of this cap problem, and I'm throwing out some ideas there. For instance, fairness considerations. So why am I talking about fairness here? So if you think about it, because we don't see the label of arms, so we sort of have to explore each one of the arms for sufficiently large time, and that has some fairness implications, and there are some notions of fairness in the online learning literature that can interestingly connect to this. And the other thing is considering worker incentives, because what happens is workers with inferior matches may leave the system, so one may want to devise a strategy that considers workers' incentives into account as well. And then obviously a natural future direction is further closing the gap between the upper and the lower bound. So that's all I wanted to talk about. Thank you again.
Thank you so much, Elia, and thank you, Anand, both for the discussion and the nice presentation. We're out of time, so I'm going to conclude the session, and we're also in the lunch break. But I encourage everyone to basically close Zoom, and then you can click on the browser window that is hopefully still open to go back to the virtual venue. And this way you can follow up with the authors and the discussants if you have any additional questions. Thank you, everyone, for attending this session.
Thank you.
Thank you all.